Okay, let's see what we remember about law of conservation of energy with this problem here, guys. So we have an ideal pendulum. Basically, that means it's operating in an isolated system and there's no friction or energy loss to anything. Okay? It is 2 meters long. It is pulled sideways and then released. At its highest point, it is 25 centimeters above the floor. At the lowest point, it is 5 centimeters above the floor. Okay? And the mass of the pendulum bob, that's the weight at the end, it's called the bob, okay, is 250 grams. So I would like you to perform a couple of, well, all 4 of those calculations that are there, okay, just to remind ourselves, how do we calculate mechanical energy, okay, and things like that, all right? So I'll give you a little bit of time to get ahead of me there, and then we'll go through them together. Okay, so a pendulum is just like a roller coaster, okay, or a kid going down a hill on a sled. As long as there's no friction, energy is conserved, okay? So they want to first off know what's the mechanical energy of the pendulum relative to the floor at its highest point. Okay, so here's what I have to recognize at its highest point. What kind of energy does it have at its highest point? Potential only, okay, because it's swinging out to the side. That's where it stops for an instant, okay? So mechanical energy is the sum of an object's potential energy plus its kinetic energy. But in that situation, it doesn't have any kinetic energy, okay? So all of its mechanical energy can be calculated by going m times g times h. All right, now things we have to remember about calculating energy. Mass needs to be in kilograms, okay, and height needs to be in meters. All right, so we're going to have 0.25 kilograms times 9.81 times 0.25 meters. Okay, so there's our mechanical energy. It is also our potential energy at the highest point, 0.613 joules. Okay, so let me ask you this. How much mechanical energy does it have right there? 0.613. Right. Does it have that much anywhere along that arc? Or everywhere along that arc? What might be the better way to say that? All right, so as long as we know that, now we can move forward with the other questions. Okay, what is the mechanical energy of the pendulum bob relative to the floor at its lowest point? That number already did that. Okay, what's the kinetic energy of the bob at its lowest point? Well, it's not that number. Why?
Because it still has some potential.
Right, it's still 5 centimeters above the floor. So it still has some potential energy. So now I've got to go EM equals EP plus EK. I know this number, it's 0.613, okay? But this number I have to calculate, and same with this number. So what I'm going to do is bring the potential energy over, because I know I can calculate that, because I know mass, gravity, and height. Okay, so mechanical energy minus potential energy equals the kinetic energy at the lowest point. All right, so that's going to be 0.613 joules minus 0.25 kilograms times 9.81 times 0.05 meters. Okay, so it has 0.4905 joules worth of kinetic energy at that lowest point. Okay, now that I know that, would it be fairly easy to calculate the speed of the pendulum there? Okay, well, I know the pendulum's mass, and I know its kinetic energy, because it just calculated that. So I could do this then. Right? I know the mass, and I just calculated the kinetic energy. So if I divide both sides by half of m and square root it, that'll get me v. All right, so 0.4905 divided by 1/2 times 0.25, all square rooted. 5 divided by 0.125, that's half of. Okay, and then square root that. All right, so just under 2. Actually, I think we only have, don't we have 3 significant digits? So 1.98 meters per second. Okay, everybody okay with that one? That one's worded a little different than the way I word mine, but I just wanted you to kind of see what sometimes a question might ask. Instead of asking what's the speed or what's the height, sometimes they want to know first how much energy it has of this type at this location, and then asks you to follow up, okay, of how fast is it going or how high is it. Everyone okay with that? Okay, I would like you guys to try this one. So we got a 3 kilogram model rocket, okay? And it's fired so that when it is 220 meters above the ground, it is traveling vertically upward, so straight up in the air at 165 meters per second. At that point, the fuel runs out, okay? So the fuel would have been doing work, okay? Now there's no more fuel. So now the energy is, well, it won't be losing it because we're assuming it's in an ideal system.
It's conserved.
It's conserved now, okay? From this point, we're assuming there's no friction, and since no more work can be done, the energy of the rocket is fixed at this point, okay? So knowing that, okay, it says assume that the effect of air friction is negligible and all potential energies are measured from the ground, okay? What's the mechanical energy of the rocket? When it reaches the highest point, what will its gravitational potential energy be? Okay, how far above the ground is the rocket at its highest point? Okay, and then also when it hits the ground, how fast will it be going? Okay, so I'll give you a few minutes to work on those and then we'll kind of go through them together. Rest assured, they're all conservation of energy questions. Okay, they're just asking you to do different things with the concept. All right, so for part A, right, we want to calculate the mechanical energy. That means add together the object's potential and kinetic energies. So that's going to be m times g times h plus 1/2 mv squared. So that'll be 3 kilograms times 9.81 times 220 meters, okay, plus 0.5 times 3 times 165 squared. That will get us the mechanical energy at kind of the initial point. Okay, so 3 times 9.81 times 220 plus 0.5 times 3 times 165 squared. Okay, so there's my mechanical energy, 47,312.1. Now, I only have, 3 significant digits there, so I would actually have to say 4.73 times 10 to the 4 joules. Okay? Now, if I'm going to use that number going forward, do I use the rounded value or the non-rounded value? Rounded value. Significant digits say if I use an answer from part A in part B, it must be the rounded value. Okay? All right. So, for part B, how much work do you have to do for that one? When it's at its highest point, it only has what kind of energy? Potential, right? When you throw something up in the air, when it's at its highest point, how fast is it going? 0. Okay, so did you already figure out the answer for part B? Because when it's at its highest point, all of its mechanical energy will be potential. So it'll have 4.73 times 10 to the 4 joules of potential energy at that point. Okay, that, guys, could be a multiple choice question. Okay, like I would tell you, hey, the mechanical energy of the rocket is this much at this point. What is its gravitational potential energy? I could give you all that information, but I wouldn't make you calculate this number. I'd make it part of the kind of the stem of the question, okay? And I would have people trying to do all the math on that when they don't have to. Okay? All right, now for part C, that I have to do a tiny bit of math for. Okay, when it reaches the highest point in its trajectory, okay, how far above the ground will it be? Okay, well, since we've just established that at its highest point, its potential energy is 4.73 times 10 to the 4 joules, I should be able to do this. EP equals m times g times h. Divide both sides by m times g, and I'll have its height. So I'll have 4.73 times 10 to the 4 joules divided by 3 kilograms times 9.81. All right, so 4.73 E4, okay, divided by, in brackets, 3 times 9.81. All right, so it should have 1.61 times 10 to the 3 joules worth, or sorry, meters. That's just about a mile. Okay, 1 mile is 1,609 meters, I think. Okay, so that is just under 1 mile above the ground. Okay, 1.61 times 10 to the 3 meters. Right? Okay, questions on how I did that part? Okay. Is D very similar to that? Okay, when it hits the ground, or the instant it hits the ground, it only has what kind of energy? Kinetic, right? When it hits the ground, because then it's all been converted to kinetic. So I think we know then how much kinetic energy it will have. Okay, calculate its speed. Okay, how many people already have it done? Okay, the rest of you, I'm going to give 1 more minute to calculate its speed when it hits the ground. So the law of conservation of energy part of D is that I already calculated the mechanical energy anywhere in the rocket's flight, including the instant it hits the ground, where it will have this much mechanical energy, all of it being kinetic. So now I can say, all right, EK equals 1/2 mv squared, right? And manipulate to get V, so divide by half of m and square root. Okay, and so what we'll plug in there is 4.73 times 10 to the 4 joules divided by 1/2 times 3, square root the whole thing. All right, so square root of bracket, 4.73 E4, okay, divided by 1.5. Okay, 178 meters per second. Right? Everybody okay with that? So worded a little differently than how I usually word it, but still valid in that it makes you have to demonstrate your understanding that once you calculate the mechanical energy, that's the number anywhere in the flight or path of that object. Okay? Okay, we did the pole vault one, right, the other day? Yeah. Okay, I want you to try that one. Okay, let's have a look at this one. So somebody's standing on the edge of a building, okay, and they throw this object vertically downward at 11.0 meters per second, and they are 130 meters above ground level. All right, all we want to do is figure out what's the speed when it hits the ground. It says velocity, but it should say speed. Okay, EI equals EF. Okay, initially, do I have both kinetic and potential energy? I have height and I have speed, so I have both. All right, so I would say EP initial plus EK initial equals. All right, at the end, when it's on the ground, it only has EK, right? Because it doesn't have any height when it's on the ground. So I can just write EK final here. All right, now I can put in my formulas. Okay, now they just said a heavy object. They didn't say how heavy. Does it matter? What can I do with mass here?
Okay.
I can cancel it, okay? Guys, I actually accidentally did that once on a unit exam. I forgot to put the mass on, okay? And I didn't realize it, and then a kid came up and asked me, Mr. Gooder, I think you forgot to put the mass on. I'm like, oh, shoot, I did. It's 300 kilograms. And then a few minutes later, another kid came up, and I couldn't remember what number I told the first kid. And I told them like 1,000, and all of a sudden there's like a bunch of kids in the classroom like, oh, does it matter what number? I could have told them 240 million and it wouldn't have made any difference. Mass cancels out. If you punch it in, it'll get the same answer. Hey, it's heavy. It doesn't matter how heavy. All right, so the mass is going to cancel. All right, then I'm gonna move the 1/2 over here, okay? And then I'm going to square root the whole thing to get VF. All right, so VF will be 9.81 times 130 meters plus 0.5 times 11 squared divided by 0.5. Okay, when we do that, we should get 52 meters per second. Okay, let me ask you a theoretical question here. This question made a point of saying the object was thrown vertically downward. Would the answer change if it was thrown vertically upward at 11 meters per second? What do you think? If I threw it vertically upward, would the answer change? I want you to think about what that object would do if instead of throwing it vertically downward, you threw it straight up in the air instead. Okay, the answer would be exactly the same. There's 2 reasons for that. First, energy is scalar. It doesn't care which way you throw it. You could throw it horizontally, it wouldn't matter, okay? It has energy because it's in motion. It makes no difference which way it's going in terms of energy. And here's the other reason. If you threw it up at 11 meters per second, all it's gonna do is go up and come straight back down. How fast will it be going when it gets back to here? 11 meters per second. Okay, that's why energy works the way it does. Energy is scalar. It doesn't matter what way it's going, that's the energy you have when it's there. If you throw it upwards, it's just going to convert that kinetic into potential and then come back down and have the same amount of energy it had if you just threw it straight downwards. Okay, strange, but true. It's counterintuitive, right? Because our gut reaction is when we throw it up, it's going to have more energy. But it won't. It's the same speed. Okay, and speed, not velocity. Okay? It actually makes no difference whether they threw it up or down. Okay? I just throw that in there to make that point. Okay? All right. I should have tried that one. We are going to assume for this that the arrow doesn't drop. We're just going to assume that it goes straight. Okay, so it's not a projectile question. In this question, I use a horizontal force of 12 newtons to pull a bow back 0.3 meters. That looks like a force and a distance being given to me. Okay? I never get that in a conservation of energy question because that does work, and work's a change in energy. All right? I know the mass of the arrow to be 0.450 kilo. That's ridiculous. That's a really heavy arrow. Very heavy. Should probably be 0.045. That might make a little more sense. This is like a pound. I'm pretty sure an arrow doesn't weigh a pound. So yeah, it's a heavy arrow anyway. Okay, what's its speed at the target 5 meters away? All right, so I'm looking for speed. When I draw back a bow, do I put mechanical energy into the bow? When I let go of the bow, does it do work on the arrow? Okay, so does all the work I put into the arrow, assuming a perfect system, get transferred to the arrow? It should, right? If I draw back a bow, I'm doing work. I'm putting elastic potential energy into the bow. If I let go of the string, okay, then the string is going to fly forward, exerting a force on the arrow over exactly the same distance. Same force over the same distance. Okay? It's going to give all the work I did to the arrow. So, if I can calculate the work, that will be the change in kinetic energy of the arrow. Because when I draw back the bow with the arrow in it, the arrow doesn't have any energy. It's not moving. All the energy is in the bow. It's when I let go of the string that now that energy does work, okay, and forces the arrow out. All right, so force times distance is going to be 1/2 mv final squared minus 1/2 mv initial, but when it's sitting in the bow, what's its speed? 0, so it doesn't have any, right? Okay, so I should be able now to calculate Vf. Okay, so 12 times 0.3 divided by 1/2 times our ridiculously heavy arrow's mass. Okay, all right, so 12 times 0.3 divided by 0.5 times 0.45. And then square root that. All right, so 4 meters per second. You'd totally be able to dodge that arrow or catch it. Okay, yeah, you could go full matrix on that one and yeah, totally catch it, not have to worry. Okay, 4 meters per second. Okay, it's very, very slow because it's ridiculously heavy. All right, questions on how that one works? A little different, right? Okay, and then I want you to do a pretty classic conservation of energy question. Okay, classic roller coaster. Okay, starts from rest at the top of a 12-meter hill. I want to know how fast it's going when it's 4 meters above the ground, assuming no friction. Okay, so pretty classic one, right? Like you got a roller coaster, okay, like this, right? We know that that first hill is 12 meters high, so that would be our initial height, right? We know that it is starting from rest, so VI is 0 meters per second. We are looking for how fast is it going here when it is still 4 meters above the lowest point. Okay, so EI equals EF. Okay, we have potential energy initial. Do we have any kinetic energy initial? Okay, so not going to bother putting that in. Okay, but we do have potential energy final because it's still 4 meters, and they're asking us for the speed. Pretty sure it's going to have kinetic energy final. Okay, I need to find the speed, which is part of that term. So I'm going to move final potential over to the other side by subtracting it, just so that I can isolate the term that what I'm looking for is in. Okay, then I can put in my formulas, m times g times h initial, minus m times g times h final equals 1/2 mv final squared. Okay, gonna cancel the m's, don't need them. Divide both sides by 1/2 and square root. All right, so 9.81 times 12, okay, minus 9.81 times 4. You could have just got 9.81 times 8 on the top and would have come up with the same thing. Okay, divided by 1/2, all square rooted. Okay, so 9.81 times 12 minus 9.81 times 4. Okay, divided by 1/2, square root. Okay, so it'll be moving at 13 meters per second to 2 significant digits. Okay, everybody good with that? Okay. On Monday, make sure you bring a pencil or two, okay, to class. That's what you will want to write the test with. Make sure you have your calculator, it's got fresh batteries in it, or it's been charged. Okay, the formulas are on the front of the test, so don't bother with your formula sheet. Okay, I will let you write into scheduled help if need be. Okay, and then obviously you'll have your marks back, and we'll go over it the next day. All right, you still have a little bit of time here, maybe. Okay, have a look over a few things like the review package or something like that. Okay, so you make the best use of your time.